Hi guys, it's Newomaster. In this video, I'm going to be talking about how my game of life works. How does it create these awesome patterns on the screen when you hit that button and mess around with the pressure pads. So, particularly I want to talk about how the pixel knows how many pixels around it are on. I mean, yeah, obviously you bus each pixel around it to it, but there's a problem with that, and I'll explain that problem after I shut this off. So, say we have a pixel right here. How many pixels are around it, are on? There's this one, this one, this one, and this one. That's 4. So what's the problem? Can't you just say how many are on, depending on how many are on here? Yes, but if this one was off, and I turned this one on, that'd still be 4. So you kind of have a problem because there are more than one way to make each number of cells around them. Now, you could have some really ridiculously complicated thing that always knows how many are on using like a decoder style system with AND gates, but that would be really big, really redundant, and really stupid. Yeah, really stupid. It wouldn't really work. It would just be massive. So what would you do? The answer is unary addition. Basically, this is a unary adder that I made. Basically, what unary addition does is it takes a number, any number of inputs, and it says how many there are in unary, which is like tick marks. 1, 2, 3. 3 tick marks, so that's how many are on. This turns out to be exactly what we need. No matter what configuration your inputs are, it always gives exactly how many there are in the same order. So I could put 3 in any possible way I could think of into this thing, and it would always return this. And I could do any other number too, just to be an example. Like 5, 8 would just be all of them on. That's 8. Now, you might be thinking, well, Nuo, this is big and giant and stupid too, because that couldn't possibly fit in a cell that small. Well, you would be right, because I didn't use this design up there. I used this one. This one is a unary adder based off signal strength addition, like I did over there. Basically, each lever adds exactly 1 signal strength. You can kind of see it. I don't know if you can see that. And adding more. So this uses the same concept of addition that I've talked about before in my videos with the binary to analog and my hex adder. It subtracts and then subtracts again from 15 to produce an output. This time it's subtracting signals of 1 each time. This happens to be a whole lot faster than this other design here. This one's about 11 ticks and that one's about 19 ticks. So this is the design I used. I pulled the output off of this right here, and I use some AND gates to determine whether the cell is on or off depending on how many are next to it. That's this line. Eventually it gets this output. And every clock tick, that piston pulses. And some people might recognize this. This is a bezel flop. It is a memory latch that updates when you hit the piston, either on or off. So if that's on and I hit the piston, the memory gate will be on. And if it's off when I hit the piston, memory gate will be off. And that's how I save the data each time the clock ticks. So basically, you input something using a pressure plate. The pressure plate is actually, I think I wired it up like this, and then the pressure plate would be here. So that's where the pressure plate is. That turns the latch on and outputs to the screen normally. And then, depending on the state of things around it, when you hit the first clock tick, it turns on or off. It calculates the next move, calculates the next cells that lived or died, next generation, and then the next clock tick, and applies that. And that goes up to the screen, and etc. Now clearing's really simple. That just blocks the bezel flop from going in a loop, and deletes the memory, sets to 0. So basically that's all there is to it. It's really not that complicated. It just looks really complicated with the size that I got it down to. I just made it really small. Most of these other lines are lines that bring the output of the memory cell to all the other cells around it, so it can calculate how many there are. So that line connects to somewhere here when you stack it, and it also connects to here, which eventually all of these lines make their way to this thing. So it powers all the neighboring cells. It's kind of difficult to see in this unstacked version because they're cut off, but if I come over to this larger stack version and I power this, you can see these lines coming out and powering the neighboring cells. Like that one turns off this, which enables the one to come out from this one and adds one. So does all the other ones that come off of this in every direction. So yeah, thanks for watching my somewhat terrible explanation on this, and I hope to see you guys next time.